In this section, we'll understand how a differentiator works. So we have a function f of x, which is depicted by this blue line. It is cut at 2 points p and q by a secant line called pq. The p point has having coordinate x and fx, and the q point is having coordinates x plus h and fx plus h. I'll explain what this h is all about. But what we want to understand right now is that this secant line is making an angle with the x-axis, which is also known as slope. And we know that this angle is basically a ratio between its y, its perpendicular, and its base. So the perpendicular is delta y, that is change in the y values, divided by the change in x-axis, which is delta x. So that's exactly what's the slope of this secant line. Now the idea here is that we want this secant line to get pushed out of this curve and become a tangent line at point P. How that can happen is if we make this delta x smaller and smaller and smaller, this q point will start sliding down over this curve. And this whole line will start getting pushed out of this function. And there'll come a point when delta x is very small, this line will only touch this function at this point, point P. And that's what is the tangent line. So that's what is the mathematical interpretation of this formula here. What it is saying is that make a small nudge in the x direction, and that small nudge is h. Basically go in this direction and see the change in the y direction, what has happened in y. So we were at fx, this was the y value, and now we have reached here, which is fx plus h. So the change here is fx plus h minus fx, which is change in the y direction. This is what is the change. And the change in x direction is x plus h minus x. So x and x cancels out, and what we finally get is h in the denominator. And the whole condition under which this secant line will become a tangent line to this point B is when this h is very small. So mathematically, this is equivalent to saying that when h starts to tend towards 0, this expression becomes the derivative or the slope of function fx at point P. And this is what is differentiation all about. Basically, it is telling what is the rate of change of this function at point P. And for this all to function, remember this h, the step in the x direction, has to be a very small one. So we will implement this whole concept in Python. Then we will take a definitive function instead of a general function like f. We will take a cosine function and see how the differentiation of cosine takes place. The second idea is once we mix some noise to this signal, to this cos signal, we want to see what is the impact on the differentiator output. So over to Python, where we'll understand all these concepts more clearly. So now we'll build a differentiator in Python. But before we do that, there's a small building block that I would like you to see. There's a function called npdiff, which we'll be using extensively to build this differentiator. So let's understand how this function works. We have an array having these kind of elements, 0, 1, 4, 9, 16, 25, etc. So if I print this array, you will see that the original array is containing these elements. My idea is that I want to calculate the differences between the elements. For example, 1 minus 0 should be 1, 4 minus 1 should be 3, 9 minus 4 should be 5, etc. So how this can be done is by using a function called np.diff and then passing on the original array in this function. And once we do that, it gives exactly what we are looking for, the differences between the elements. So here we are, this is the output. So 1 minus 0 is 1, 4 minus 1 is 3, 9 minus 4 is 5, and so on and so forth. So this function is a very important function. As you remember that change in y-axis and change in x-axis is what we are looking for. Our x-axis is going to be a very small increment, so that's going to be a fixed constant. But change in y-axis is going to be calculated using this particular function. So let's get started. Let's define. So if you remember, we have to create a cosine function. So to do that, I'll specify some signal parameters first. Firstly, my signal should last for 1 second. The sampling frequency of my signal is 1000 hertz. So obviously my sampling time will be inverse of this, which I'll call as dt. And the amplitude of this signal is 1 volt. And frequency of this signal is, let's say, 2 hertz. So now I'll generate the time axis by using this function called time, t, np arrange. Essentially, I'm going to start from 0 seconds. I have to, if you remember, we have defined the time duration of the signal, which is t. So I have to go till t. And in how many steps? I have to go in steps of dt, the sampling time. So if you, I'll just print out this t. So here we are. We'll start from 0 seconds and we'll go to 1 second. And our sampling time is 0.001. So this is what is being shown here. This is the smallest time step increment that we have. So our time axis is created. I'm going to remove this print statement from here. And let's generate the cosine signal that we are looking for. So let me call it signal, and I will use a function called cos, and I'll fill in the parameters. But before that, the signal has an amplitude, so we multiply it by the amplitude. Then 2 pi ft. So this is 2 pi, the frequency of the signal, into the time axis that we just created. So this is where we are. Instead of calling it t, let me just call it time so that it becomes clearer. So this is our signal, and let's have a quick look at how this signal looks. So let me just plot it. So time is my x-axis and my signal is my y-axis, and let me activate my general plot settings here. So let's see how this signal looks. So there we are. It's a 2 Hz signal, so there are 2 complete cycles of this cosine wave starting from 0, 0 to 1 second, and the amplitude is 1 volt as seen, plus minus 1 volt as seen here on the y-axis. So we are successful in generating our clean signal, and now we want to differentiate this signal to see what kind of outcome gets generated. So let's call it differentiated signal, and remember I'm going to use that NP diff function here, which is a change in y-axis, and I'm going to pass on this signal to this function, and I have to divide this whole, this is a numerator, this is change in y-axis, and I have to divide this by change in x-axis. So my change in x-axis is equivalent to the time step, which is dt. So I'm going to do that, and let's have a look. So the theory says that if you differentiate a cos signal, you will get a sine signal. Let's see if that is happening or not. So again, we're just going to plot it. My x-axis is time, and my y-axis this time is the differentiated cos signal. And clearly, we have run into an issue, and that issue is mismatch in array sizes. So how we can fix it? Essentially, my time axis has got 1000 elements, but my signal, differentiated signal, has got 999 only. So that's why there's a problem. So we are going to correct it by indexing it properly. And how we are going to do it is we're just going to take the first 99 time points, 999 time points, and forget about the last one. So how that is done is like this. So I've discarded my last time point in the time axis so that both these arrays have 999 points to plot. So there we are. And as we can see that we have been able to generate the negative sine signal from the cosine signal, but its amplitude is very large. And that's because we have not done the scaling properly. In fact, we can go back and see the original signal if you want to have a look at that, which was the cos signal. So let me just time axis and signal. So here we are. Our original signal was cos signal, which was fluctuating between -1 and +1. So it's a very small signal. But what has come out of this differentiator is definitely a minus sign signal, but it is scaled up in its value. So we have to correct it by a scaling factor, and that scaling factor, let's just call it scale, and it is nothing but 2 into NP pi by the frequency of the signal. So this is a scaling factor. So let me recalculate my differentiated signal again. So differentiated signal or function will be nothing but the scaled value of this. And let's plot. Okay, so there's an error, and this should not be a dot. It should be a multiplication sign. So here we are. Now you can see that both the signals are now fluctuating between +1 volt and -1 volt. They have been scaled properly. This blue is the cos, the original signal, and the differentiated signal is minus sign. So the phase reversal has taken place, and it is basically a flipped sine wave fluctuating between 1 and -1. So in this way, we have been very successful in implementing the differentiator. But let's go further and understand what happens if my original signal, has some noise. So how I'm going to implement that is by generating some Gaussian noise. Let the mean of that noise be 0, and let the standard deviation of that noise be 0.1. And let me generate that noise using NumPy's random.normal. So this generates pseudo-random numbers from Gaussian distribution with mean 0, standard deviation we have already defined, 0.1. And how many number of such points do we need? As many points as the original signal has, because we have to mix this noise with the signal. So as many number of points. In fact, we can define that here, number of points, which will be equivalent to the length of the original clean signal. So here we'll just simply say n, and let's see how this noise looks now. So we're going to plot this. We have time axis, we have noise here. So let's see. So here we are. This is Gaussian noise, Gaussian distributed noise. As you can clearly see that it is fluctuating between 0.1 and -0.1 more frequently than other values, other extreme values, and it is centered at 0. So mean is 0. We are going to take this noise and mix it with our original cosine signal and see what happens when we pass that signal through the differentiator. So I'm going to disable this, and how I'm going to add this noise is very simple. I'm just going to say this is a noisy signal, signal plus noise. So all I have to do is just say signal plus noise, and let me just plot this and see how it looks. So my time axis and my noisy signal, and let me just also plot the other two plots. So here we are. So as you can clearly see that my original signal, which is now buried under this, has got corrupted by this high frequency noise. In fact, I can just make this noisy signal slightly transparent so that we can see the, it is too light, so let me just take it to, here we are. So the original cos signal is here, which has got now buried under this high frequency noise, and this is the differentiated cos signal, which we are still getting it here. But idea is to see what happens when we differentiate this noisy signal. What happens then? So over to that. Let me just disable this plot and also these two plots. And again, I'm going to make another differentiator exactly on the same principles as I did earlier. So I'm going to say I have to take this noisy signal, signal plus noise. So let me call it differentiated signal, noisy signal. And I'm going to again going to pass it through the differentiated series divided by change in the x-axis. And again, we have to have a scaling factor here. So I have to correct it for the scaling factor by dividing it by the scale, which we calculated here. This is the scaling factor. So let's understand what happens when we have when we differentiate a signal which has mild amount of noise. So let's see that. So time axis, and again, since we have differentiated here, we are going to get only 999 points. So I have to get rid of the last point, otherwise I'll run into indexing problem. And my differentiated noisy signal, and let's just plot it. And let me just, so that's pretty surprising that I have only got amplified noise. What has happened here? And you can see that this output is varying from minus 20 volts to plus 20 volt. Whereas our original noise was just about 100 millivolt, 0.1, if you remember, plus minus 0.1. Now this has become plus minus 20 and even exceeding it. So what has happened here? So it so happens that differentiator acts as a noise amplifier. Let's just play around with this noise a bit and see what is the impact. So here we had generated this noise, and let's say we reduce this noise by a factor of 10. So you can clearly see that the underlying sine, minus sine wave is appearing here, but still there's a huge amount of noise that has got amplified on top of it. So this is clearly, even with a very small amount of noise, actually if you see noise now, it will be a very small amplitude. So let me just activate that plot. Here it is. It is so small that you can't even see it. But on the sine signal, it has been, on the output of the differentiator, it has been amplified a lot. So the lesson learned is that a differentiator acts as a noise amplifier, especially if a very high frequency signal is riding on a low frequency signal. The low frequency signal will get filtered out because the differentiator is acting as a high pass filter. And unfortunately, the small noise that was riding, high frequency noise that was riding on the low frequency signal, that will get amplified. So that's the whole issue. And let me just disable all the plots wherever. Here too. So I'm going to activate my original plots here. So let me just summarize what we have done so far. So we had this cos signal, the original signal, original function, and we passed it through the differentiator. If you notice, the original cos signal is varying between 1 volt to minus 1 volt peak to peak, and then I take the signal, I pass it through a differentiator, and what I get is the sine wave minus sine. So this is the sine wave which is flipped. As long as my signal was clean, there was no noise on top of it, I've got perfect output from the differentiator. It is giving me exactly what is written in the theory books, that if you differentiate a cos function, you will get minus sine. So far so good. But in real systems, this does not work, because in real system we have noise, and we have noisy signal to deal with. And if we use differentiators, especially at the front end of the receiver, then this noise component is going to get amplified drastically. So if you see here, I'm just going to now plot the noise, And you see this noise is extremely small. This is what I'm generating. In fact, I can increase it a bit to the original. So my standard deviation goes up. And this is the noise. Now you can see it very clearly. It is varying between 250 millivolt plus to minus 250 millivolt. In fact, lesser than that. Now I'm going to put this noise on my original signal, on this cos signal. So this is the noisy signal. So now you can clearly see that my original cos signal, blue, has got hidden behind this noisy signal. In fact, I can change the transparency here so that you can see the original signal. Here we are. So this blue was my original clean cos signal, and on top of it, I have added this green colored noise, which is being shown here by red color. It is fluctuating. And then I want to now see what is the output. So I'm going to disable my plot of clean derivative of cos, and now I'm going to see the derivative of the noisy signal. And unfortunately, you see that the noise has got amplified. You see these red spikes, they are going above almost minus 30 to plus 30 to minus 30. And this is the issue with the numerical differentiators. If we have a signal which has even small amount of noise on top of it, and if we pass it through a differentiator, which acts as a high pass filter, so you see that these original signals have disappeared because they were low frequency components, and the noise, which was a high frequency component, has got amplified by this differentiator. So that's the learning from this this tutorial. In fact, we can just play around with this noise a bit, and we can see how the, let's make the noise even smaller. So you see it has become very small now, and yet my output signal is having very, very big spikes, which is amplified noise. It is riding on the underlying minus sign signal, but it has been amplified drastically. If we reduce this noise further, so you start to see that underlying integrated differentiated minus sign function, but with enormous amount of noise riding on the output of the differentiator. So that's the reason why we don't use differentiators upfront wherever low noise requirements are there, especially in filtering or in low noise receiver designs.